Okay guys, I'm going to do a quick little lesson on 2D momentum. I'm going to do one example for you. We'll do more of this in class. But conservation of momentum in 2 dimensions is just like conservation of momentum in 1 dimension. So for example, if we have an object with a mass of 2 kilograms that's moving at 3 meters per second at an angle of 25 degrees west of north, so 25 degrees west of north, and this object has a mass of 2 kilograms and is moving with a speed of 3 meters per second. We say it has a momentum of 6 kilogram meter per second, but what's the direction? Well, the direction is 25 degrees west of north. So the momentum of this object is 6 kilogram meter per second. So this momentum, since it's a vector, has components, right? It has components that point north and component that points west. So we have a northward component and a westward component. And we'd find the size of these components just like we would any other vector components. The northward component would be 6 kilogram meter per second, and that would be the adjacent side to the triangle. So cosine 25 degrees. Which is 5.44 kilogram meter per second. Of course, the same units because this is a component of a momentum, so it is a momentum. And this guy would be 6 kilogram meter per second times the sine of 25 degrees, which is 2.54 kilogram meter per second. Now, if this object collided with some other object that had some momentum at some other angle, we could find the components of that object's momentum, and then we could add up the components, and the x momentum and the y momentum would have to be separately conserved. And then we could recompose those momentums back into triangles to get final momentums for each object. So here's our first example of this. So we have object A, which is moving in this direction at 3 meters per second, and it's a 5 kilogram object. And it collides with object B, which is at rest. And object B has a mass of 2 kilograms. Okay, so we could see that the overall momentum of this system is plus 15 kilogram meter per second. And that will be the overall momentum after the two things collide, whether it's a totally elastic collision or an elastic collision or whatever. The total momentum of this system has to be 15 kilogram meter per second to the east. That means any north and south momentums that do happen have to cancel each other out. The total north and south momentum at the beginning is 0, so the total north and south momentum at the end is 0. So the sum of the momentums in the y direction is going to be 0 here, and the sum of the momentums in the x direction must be plus 15. Okay, so let's break this into x's and y, like an x area and a y area. So we could say that the momentum, so the p1x plus p2x is equal to p1x prime plus p2x prime, and p1y plus p2y is equal to p1y prime plus p2y prime. Now after these two guys collide, what happens is we have object A going off in some direction like this, and object B going off in direction that we specify. So object B is going at 30 degrees south of east, and it's got a speed of 4 meters per second. Okay, well that momentum, right, has components. It has the momentum of object B is 8 kilogram meter per second, and it has a component to the east and a component to the south. So the eastward component of that, 8 kilogram meter per second times the cosine of 30 degrees, is 6.9 kilogram meter per second. And the y component, 8 sine 30 degrees, we could say is negative 4 kilogram meter per second. We're picking negative because we're making south our negative direction. So, if we come back here and we start filling this in a little bit, so P1y, so there's no y momentum for this object initially. And there's no y momentum for this object initially. So the momentum before in the y direction is 0, and that's equal to the momentum of this guy in the y direction after, P1y prime, minus the momentum of this guy in the y direction after, negative 4. So we're going to bring this guy over. P1 y prime is equal to plus 4 kilogram meter per second. And that's as we would expect, right? The northward component of this guy's momentum must be plus 4. Why? Well, because we had 0 y momentum to start with, so we have to have 0 y momentum after the collision total. What about in the x direction? Okay, well in the x direction we had P1x is 15 plus 0 equals, now the P1x we don't know yet, right? P1x prime plus P2x prime, well we found out that was 6.9 kilogram meter per second. So P1x is 15 minus 6.9, or 8.1 kilogram meter per second. So now we know that this guy's momentum in this direction was 8.1 kilogram meter per second. And if we look, there was 15 units in this direction. There are 15 units in that direction still. 0 units in this direction. So all we have to do now is figure out what's going on with object A, right? Well, we have 2 momentums, 8 kilogram meter per second that way, and 4 kilogram meter per second this way. And this obviously forms a right triangle, and we can find angle theta using our inverse tan function. Theta equals inverse tan of 4 over 8.1, which is about 26 degrees. And if we want to know the actual momentum, well, that's equal to the square root of 8.1 squared plus 4 squared. So the actual final momentum is 9 kilogram meter per second. And if we want to know the velocity, well, P equals mv. So we divide this by the mass of object A, which was 5 kilograms. So 9 equals 5v. V is 1.8 meter per second. So we have our final answer. Object B goes off at 30 degrees at a velocity of 4. Object A goes off at 26 degrees with a speed of 1.8. So hopefully you can see that this is really nothing that much more complicated than what we've done with triangles. It's just vectors adding up into right triangles as before. We can get more complicated by introducing more angles and more things going in different directions, but really other than that, you just need to keep your total x and total y accounted for and make sure that the total at the end is equal to the total at the beginning.